Okay, today's notes, we're going to talk about confidence interval, the t-interval. So let's look at an example. In a randomized comparative experiment on the effects of calcium on blood pressure, researchers divided 54 healthy white males at random into two groups, one that takes calcium or one that takes placebo. Paper reports a mean seated systolic blood pressure of 114.9 with a standard deviation of 9.3 for the placebo. Assume that systolic blood pressure is normally distributed. So can we find a z-interval for this problem? Well, to find z, we need to know that it's normal. It is normal. We need to know that it's random. It does say random. But we need to know the population standard deviation. Do we know sigma, the population standard deviation? And no, we do not. Notice that the standard deviation is only from the 54. So z cannot be used. We have a sample standard deviation. Therefore, our z-interval can't be used as sigma is unknown. So we need another test, which is where the t-distribution comes into play. It is developed by William Gossett. It is a continuous distribution. It is a unimodal, symmetrical, bell-shaped density curve. It is above the horizontal axis. And just like z, the area under the curve still equals 1. But difference between z and t is based on what we call degrees of freedom, n-1, which is sample size -1. So if we graph examples of t-curves as normal curves, notice our blue z is our pretty nice symmetrical normal curve. And notice that t is going to change based on sample size. So the smaller the sample size, the more variability we're going to have and the more flatter of a curve we're going to have. So how does it compare to our normal z distribution? It is shorter and more spread out, or more variability. It has more area into the tails. All the area is still 1, but notice you got more area in the tails as opposed to closer to the middle mean. As n increases, t distributions become more like a standard normal distribution. So t changes based on your sample size. It is not fixed. Your z curve is what we call fixed. So how do we find our t statistic? We have a separate table for it. So if you open up your AP formula sheet, your first two tables are your z tables for positive, negative. The next two are your t tables. Look up the confidence level at the bottom and degrees of freedom on the sides. Remember, degrees of freedom is your sample size -1. So let's practice finding these t critical values. So if we want to find a 90% confidence when n equals 5, so look at the horizontal confidence level, find 90%. Zoop, go up. If our sample size is 5, degrees of freedom is 5 minus 1, so 4. So that t critical value is 2.132. If we're trying to find 95% confidence when n equals 15, again, horizontal, find 95% confidence. Zoop, go up. Degrees of freedom would be 15 minus 1, so 14. So 14 and 95% would give us a t critical value of 2.145. So formula for our t confidence interval. Again, we have our estimate, our sample mean, plus or minus. Only thing that changes is that we have our critical t value found by the t table, or we're going to have the calculator do it for us, multiplied by your standard deviation of the sample, so little s, divided by square root of n, your sample size. And your margin of error, again, is your critical value times your sample standard deviation divided by square root of n. But good thing is we can also let the calculator do the work. So if you don't want to write out formula, again, we can find it on the calculator by stating menu, statistics, confidence interval, t-interval. And again, you're going to choose stats if you have the mean, the standard deviation. If you have actual data values, you're going to use data. But if you're not using the formula and writing the formula, here is how you show calculator work. You have to write CI, name this test, the t-interval, and parenthesis, everything the calculator asks for. Make sure to label your variables. Assumptions for t-inference. You must check and write down before starting. So you must have an SRS, must state SRS, or nothing assumes otherwise. You have to have sigma unknown. You have to have the sample standard deviation. And you have to have that it is normal or approximately normal. So that could be stated. It could be a large sample size and greater than 30. Or we could make a box plot on our calculator and show that it is approximately symmetrical box plot. So going back to the very first example I presented to you on these notes, we are to find a 95% confidence interval for the true mean systolic blood pressure of the placebo. So in a randomized comparative experiment on the effects of calcium on blood pressure, again, we took 54 healthy males and put them into two groups, one that takes calcium, one that takes placebo. And the paper reports a mean systolic blood pressure of 114.9 with a standard deviation of 9.3 for the placebo. So assume that systolic blood pressure is normally distributed. So before we can find a confidence interval, we first need to check assumptions. Is it an SRS? Yes, it's stated random, that is check. Is it normal? It's stated normally distributed, but also our sample size n is greater than 30. So by both methods, it is check. Is sigma unknown? Well, yes, that checks because notice this says from the standard deviation, from the sample, it has a standard deviation of 9.3. So we can either calculate using the formula or the calculator. If you calculate the formula, your mean is 114.9 plus or minus. This is found from your T table. Again, degrees of freedom, if it doesn't include 53, just do the largest number. Times your sample standard deviation, 9.3, divided by square root of n, 54. If you're using the calculator, again, you need to name CI, T interval, everything the calculator asks for, including variables. But a confidence interval is not done until you write an actual sentence. So we are 95% confident that, what are we talking about? Use the wording in the sentence. True mean systolic blood pressure is between our lower and our upper, 111.22 and 118.58. This is what you call a full write-up. Must have assumptions, must have equation work or calculator work with sentence. So robust, an inference procedure is robust if the confidence level or p-value doesn't change much if the assumptions are violated. So our confidence interval and p-values deal with area in the tails. It is the area changed greatly when there is skewness. And since there is more area in the tails in a t-distribution than if a distribution has some skewness, the tail area is not greatly affected. So t procedures can be used with some skewness as long as there are no outliers. So this is the advantage of the t-interval as opposed to the z. Z, you cannot have any skewness at all. T, again, because it allows for a little bit more variability, slight skewness can occur as long as, again, no outliers. And larger sample size n can have more skewness. Because as we talked about, again, always if you increase your sample size, you're going to get a more towards the normal looking curve. So let's look at another example. A medical researcher measured the pulse rate of a random sample of 20 adults and found a mean pulse rate of 72.69 beats per minute with a standard deviation of 3.86 beats per minute. Assume the pulse rate is normally distributed. Compute a 95% confidence interval for the true mean pulse rates of adults. So as always with confidence interval, must state assumptions. So we're first going to, we need to check, is it an SRS? Stated random, that checks. Is it normal? Stated normally distributed, so that one checks. Is sigma unknown? That checks, because notice our standard deviation is only from the 20 adults. So once we check our assumptions, we can proceed. Again, you can either use the formula equation, or if you're using calculator, CIT interval, write out exactly everything the calculator asks for. And you are not done until you write a sentence. We are 95% confident that the true mean pulse rate of adults is between 70.883 and 74.497. So what if another medical researcher claims that the true mean pulse rate for adults is 72 beats per minute? Does the evidence support or refute that? Well, the 95% confidence interval contains the claim of 72, therefore there is no evidence to doubt. So if we go back to our interval, notice 72 is within this realm. So since it is in the interval, there is no evidence to doubt it. You would doubt it if it was not in the interval. So one last example, we have a set of numbers here. Compute a 98% confidence interval for the average calorie content per serving of vanilla yogurt. First, you must check assumptions. Is it an SRS? It is stated, check. Is it normal? Well, if we have data points, we actually need to create a box plot, okay? So on your calculator, input the data values, make sure to label the column, put menu quick graph and change to box plot. You should see that the box plot should be approximately symmetrical, about even whiskers. Is sigma unknown? Well, yes, because all we have are data points, right? And the calculator can actually calculate that standard deviation for us of the sample. So input all the data values into your list in spreadsheets. Go to menu, stats, confidence interval, t-interval. Again, change to 0.98 because we're finding 0.98 confidence level. And showing your work, again, you'll have to get these values from the actual output. The calculator output will tell you the sample mean and the sample standard deviation. So that's how you have to look at it for your showing work calculator. And then finally, you must end with a sentence. We are 98% confident that the true mean calorie content per serving of vanilla is between 126.16 and 189 calories. So if a diet guide claims that you will get 120 calories from a serving of vanilla, what does this evidence indicate? Let's go back to our interval. Is 120 in here? No, 120 is not in there, right? So since 120 is not contained within the 98 confidence interval, the evidence suggests that the average calories per serving does not equal 120. The answer is no if it's not in the interval. The answer is yes if it is. So confidence intervals tell us if something is not equal, never that it's less or greater than. Okay, you can't say, oh, it's below it, so it's less. You can only say it's not equal. So some cautions. The data must be a SRS from a population or randomly assigned treatment. The formula is not correct for more complex sampling designs, i.e. stratified. And there's no way to correct for bias in data. Outliers can have a large effect on confidence interval. And we must know that our standard deviation to do as the interval, the population standard deviation, which is unrealistic in practice. So that concludes our confidence interval for our t interval.